Hey there, in this video we're going to continue exploring curve sketching and following the steps, finding the domain, finding asymptotes, x-intercepts, y-intercepts, and determining the intervals where a function is increasing, decreasing, concave up and concave down to sketch the graph of the function. So let's start with the domain. So always when you're about to sketch the graph of something, what is the domain? And so let's see, this function, the domain is this ever undefined. Notice that because of the negative exponent, we can say this is x squared over e to the x. So this is never zero. E to the x is never zero. And so everything is positive and never zero. So the domain is all real numbers. This is never undefined. We have no radicals, the denominator is never zero, and we have no logarithms. Those are the functions that restrict the domain. So what about x and y-intercept? X-intercept is we set y equal to 0 and solve for x. So we're going to have 0 equals x squared times e to the negative x. And so you solve for x, which in this case just tells us x is 0. And so our y-intercept is we set x equal to 0, but as we see here, we're going to get y equals 0 also. So our x and y-intercept are the same, and it's 0, 0. Now let's look for asymptotes. We want to look for, are there any vertical asymptotes? Are there any horizontal asymptotes? Are there any slant asymptotes? And this function has no vertical asymptotes. The denominator is never 0. So no vertical asymptotes, or the domain is not restricted. So no vertical asymptotes, but let's check horizontal asymptotes. So for horizontal asymptotes, how do you find them? We take the limit as x goes to infinity and to negative infinity. So this one I'm going to do them separately because we have an e to the negative x here, so they'll likely go to different places. So I have x squared e to the negative x, which we can write it the way that we did above. So it'll be x squared over e to the x. So as x goes to infinity, you have the form infinity over infinity, which means we can use L'Hopital's rule. And so we can say then this is the limit as x goes to infinity of 2x over the derivative of e to the x, it remains e to the x. And I still have infinity over infinity, so we can use L'Hopital's rule again, and I'll have the limit as x goes to infinity of 2 over e to the x. And so now as x goes to infinity, you have 2 over infinity, which is going to go to 0. So we have a horizontal asymptote at y equals 0 as x goes to infinity, so on the positive side. What about as x goes to negative infinity? Of x squared over e to the negative x, e to the x. And in this case, do we even need to rewrite it? So let me go back and leave it the original way that is written, x squared times e to the negative x, because what's going to happen here is you're going to have negative infinity squared, that's positive infinity, right? And then negative infinity e to the negative and negative is really e to the positive infinity, which is infinity. So you have infinity times infinity, which will be infinity. So we have a horizontal asymptote to the right. As x goes to positive infinity, the y values go to 0, but as x goes to negative infinity, so on the left of the axis, of the x-axis, they're not approaching a specific y value. They grow without bound, so they go towards infinity. So we can start plotting some of our information. So we already know our x-intercept and y-intercept is 0, 0, and we know that we have a horizontal asymptote here at 0. So y equals 0, that horizontal line, the x-axis essentially, is a horizontal asymptote to the right, and to the left, as x goes to negative infinity, the function grows without bound. It goes towards positive infinity. So now let's look at the increase and decrease, which is the fourth step. So we know that our function is x squared e to the negative x, so find the derivative to find critical numbers. So that means we need to use the product rule. You have x squared times e to the negative x. So product rule says the derivative of the first, so 2x times the second left alone, plus the first, which is x squared, times the derivative of the second. And let's simplify that. Can we factor anything out? We can take out an x and an e to the negative x. And when we take those out, what are we left with? We're left with 2 minus x. And when you set it equal to 0, then we get a critical number. This one, x is 0. This is never 0. And this is 0 when x is 2. So we get 2 critical numbers. So let's do our number line, or you can do the table of intervals. And so I'm going to put here 0 and 2, and we're testing the first derivative. So f prime, and this is where the derivative is 0. So these are possible what? Local max, local min, or saddles, right? Local max, local min, or saddles. And so let's see, depending on what the derivative does, that tells us what the function is doing. If the derivative is positive, the function is increasing. Now here, we can kind of guess what's going to happen, because I see that we have to cross here. So at some point, this function has to decrease. So I'm kind of guessing based on my limits that my first interval from minus infinity to possibly 0, we're going to be decreasing. So, but always check it. So let's find our test points. And we're checking the first derivative. I'm going to use the simplified version, x e to the minus x and 2 minus x. So what can we pick between negative infinity and 0? You can pick x equals like negative 1, for example. And so f prime of negative 1, and again, we don't necessarily care too much about the value, but the sign, is it positive or is it negative? So when you plug it in, we're going to have a negative. E to the x and e to the minus x are always positive, so that's positive. And then 2 minus a minus 1, so that becomes 2 plus 1, which is positive. And so I have a negative times a positive is negative, which is what I expected based on the limit. So the derivative is negative, so that means the function is decreasing. Now between 0 and 2, what happens? So it's either gonna, if it decreases, we're gonna have a saddle, but if it increases, we're gonna have a local min there. So pick something between 0 and 2. Let's say x equals 1. So the derivative at 1. So now we're gonna have positive. E to the minus x is always positive, and then 2 minus 1 is positive. So everything is positive. So my derivative here is positive, which means that the function is increasing. So what do we have at x equals 0? We have a local min. 0, 0. And I know the y value there because we found it as the x and y intercept. If I didn't know it, so like for 2, we're going to have to find the y value there. So now between 2 and infinity, let's pick a test point. So let's say x equals 3. So f prime of 3 will be 3, so that's positive. E to the minus x is always positive. And then 2 minus 3. So now that's going to be a negative. And so I'm going to get negative. So the derivative here is negative, which means that the function is decreasing. So what do we have at 2? You're going to have a local max at 2 comma f of 2, right? Original function, f of 2. So we'll have to figure out what that is. Well, I guess we can do that. F of x was x squared e to the minus x. So f of 2 is 4 e to the minus 2, or 4 over e squared. So that is your local min, or local max value. So we can replace that. So you have a local max at 2 comma 4 over e squared. And so you could plot that over here. So now I know this is a local min and at 2 and what was it, 4 over e squared you're going to have, which is very low. So here 2 and 4 over e squared, you're going to have a local max. So I know this is going to do something like that, and this is going to do something like that. So we can then graph what we think the function looks like so far with just the increasing and decreasing. So I know it decreases from minus infinity to 0, and then it increases from 0 to 2, and then it decreases from 2 to infinity. So it's going to decrease all the way here, then increase, and then decrease again. But how does it decrease, right? Does it go like this, decreasing, or does it go like this, decreasing? So that's where the concavity comes in. So let's go explore the concavity. So f double prime of x is, we need to find it. So let's write what our derivative was. Our first derivative was x, e to the minus x, and 2 minus x. So I have 3 functions being multiplied, so there's a triple product rule for the second derivative. So then it's going to be the derivative of the first, which is 1 times the second left alone times the third left alone, plus the first times the derivative of the second times the third left alone, plus the first left alone, the second left alone, times the derivative of the third, which is -1. And is there anything we can take out? We can definitely take out the e to the minus x from all 3 terms. So let's start with that. So e to the minus x, and this becomes, let me make that a bracket. So I'll have the 2 minus x plus, actually minus, right? Because we have this negative here. So negative times x becomes a negative x, 2 minus x, that, leave that in parentheses, and then minus x. And so let's simplify that middle part. I was just trying to see if there was anything else we could have factored out, but doesn't look like it. So 2 minus x minus 2x plus x squared, and then minus x. And simplify that some more. Now I'm getting a quadratic in there, so let's see. So I'm going to have positive x squared, and then minus 2x minus x minus x, so what's that? Minus 4x plus 2. And now we can set this equal to 0 and solve for x. Well, this is never 0, so we don't have to worry about that. So it's just set this equal to 0. So x squared minus 4x plus 2 equals 0. Does this factor? Can we find 2 numbers that multiply to 2 and add up to -4? No, but just because it doesn't factor, it doesn't mean it doesn't have a solution. We can use the quadratic formula. So a is 1, b is -4, and c is +2. So the quadratic formula tells me x is the opposite of b, so +4 plus or minus the square root of b squared minus 4ac all over 2a. 2 times 1 is just 2, and then simplify that. So 4 plus or minus, what's this, 16 minus 4 times 2 is 8, so 16 minus 8 all over 2. And so that gives me 4 plus or minus the square root of 8 over 2. And be careful, right? You don't want to say like, oh, I can cancel this, 4 and 2 cancel out. You can't do that. Why not? You can't, this is still being added and subtracted from this quantity. You have to simplify the whole numerator before you can divide with anything in the denominator. So, and this is +8. I don't know if my pen just went crazy or if I actually wrote a -8. So, and the square root of 8 is what? The square root of 4 times 2. So we can simplify. The square root of 4 is 2. So then this becomes 4 plus or minus 2 root 2 over 2. And now I can cancel out the 2, right? Because now this 4 and 2 have a common factor of 2. So I can take that out. And now I can say, oh, now I can cancel these because this 2 is times that quantity. So it's being multiplied. When it's just the 4 is being added, I can't cancel like that. You have to have multiplication. So my candidates for inflection points are 2 plus or minus root 2. Which ones you separate them is 2 plus root 2 and 2 minus root 2. And we can test them. So which one's which? Well, 2 minus root 2 is the smaller one, and then 2 plus root 2 is the larger one. And this is where the second derivative, we're going to see what it does. And based on that second derivative, we're going to know information about the function, the original function. And this is where the second derivative is 0. So let's try some test points. So notice that right smack in the middle of 2 minus root 2 and 2 plus root 2 is 2. So I'm going to be able to use 2 as the test point for the middle. But let's try minus infinity to that. So my second derivative, this is what we're testing, was e to the minus x times x squared minus 4x plus 2. And so our test points, pick 0 likely, because that's a nice one to use. When x is 0, you have e to the, well, this is always positive regardless of the value of x. E to the minus x is always positive, right? Because the negative on the exponent just means it's 1 over e to the x, but in e to the x is always positive. So when x is 0, this is positive, and then 0, 0 plus 2, so positive. And it's positive. So we're going to be, second derivative is positive on that interval. So what does that tell you about the function? Sad face or happy face? It is concave up, so happy face. And then a test point between 2 minus root 2 and 2 plus root 2, we can pick 2. That's right in the middle of those two. So that's always positive. So then 2 squared, that's 4 minus 4 times 2. So 4 minus 8 is negative 4 plus 2, so that's negative. And so that means that the second derivative is negative, which tells us that the function is concave down, curves downwards. And what do you think is going to happen on the other side? So let's pick 4 just to be sure. So e to the negative x is always positive, and now when you have 4 squared, that's 16 minus 4 times 4 is 16. So 16 minus 16 is 0, so you're left with a plus 2, so positive. So second derivative here is positive, which means that the function is concave up again. And so now we know how to finish the graph. We knew it was decreasing, but we didn't know how it was decreasing. Now we know that it decreases and it's curving upwards. So it's concave up all the way through here. And then at some point it changes concavity, right? So here is 2 where our local max is. So 2 minus root 2 is somewhere over here. And so that's where concavity changes, and then it comes back down. So let me clean up my graph here so I can graph it. So, and this is not going to be to scale, but so it does something like that. So we have our local min here, and then this is changing concavity somewhere over here, right? So this is our point of inflection. So this is likely the 2 minus root 2, and then it changes, notice that is concave down, and then it changes concavity again at our other point of inflection, which is likely 2 plus root 2. And so you have is concave up and then concave down and then concave up again. And so it's decreasing, increasing, and then decreases again. So this is the max, local max, and this is the local min, right? Relative max, relative min. This has no absolute maximum because it grows on forever, but and it also does not have an absolute minimum. It gets really, really, really close to zero, but it never attains it. So that's what our graph looks like. So this is, hopefully you can see better how you can kind of tell what the graph is doing from the increasing, decreasing, but concavity really helps you figure out what exactly the graph is doing, right? We know it's decreasing, but we want to know which way. Is it curving upwards or is it curving downwards? So that's where concavity comes in. All right, I'll record another video for the last two examples.